lot of materials around, which is one of the reasons why we use concrete. There are also other reasons, such as concrete has good strength for various applications. Right now, we have ultra high performance concrete. We can get above 100 MPa concrete. So that's one of the main reasons why we use that material. Another reason is because we can recycle concrete now. Compared to things like plastic, it is non-flammable. Compared to wood, it is rot-proof, which means it doesn't rot. Compared to steel, it is rot-resistant. And also, concrete is very water-safe. And this is one of the reasons we could actually use concrete for various applications in water infrastructure, like dams and drainages. Concrete also has a good thermal mass, it's not flammable, it's insect proof, and does not release any volatile organic emissions, which is really great. And this is really one of the reasons why we're using concrete on a large scale. In addition to this, concrete also has a lot of properties, which result in us using a lot of this material. As we know, depending on how we design concrete, concrete could have a very good durability. Also, due to the fresh nature of concrete, it's very versatile. So, which means we could have columns, slabs, various structures of various shapes. So, with all this performance, this has resulted in us really using a lot of this material, which makes concrete the most used construction material in the world. And this is evident. I would say, like, literally everywhere we go, we are going to see these. There's concrete everywhere. We can't really do without concrete. Concrete is really evident everywhere. Looking at the towers in Malaysia all the way to Canada, and we also have like even a new bridge currently in Canada we're constructing, which is going to connect Canada with the US. So concrete is a material that we can't really do without. It's very essential, and these actually play a key role in sustainable development. There are actually few building materials that can really have significant impact on sustainable development. Concrete, on the other hand, has really huge impact on sustainable development. So, for example, the way we produce the cement, the way we produce that concrete, the way we mine the resources could impact the environment. The emissions we put in the environment could impact the environment. And also, as we know, the cement industry, the concrete industry are actually one of the major contributors to the economy. So, on the positive side, this is very good. And again, concrete can be used for social progress. We have the construction of bridges, roads that join different people together. So concrete as a whole is very critical to sustainable development. In fact, looking at all the 17 sustainable development goals we have, concrete alone contributes to about 5 of those, which is really huge. So concrete is an essential material that we have to use. This is really important for sustainable development, but we should also take note that we're using a lot of this material. If we compare concrete itself to other construction materials we have, you can see in this figure I have here, concrete on its own has a very it has a very low embodied carbon compared to other construction material. But the issue with concrete as a material is that we use too much, as I show in the first slide. Because we use too much of this material, it means at the end of the day, we have more carbon emission from the production and use of this material. So if I should kind of break this down, and we know a traditional concrete has a coarse aggregate, fine aggregate, cement, water, and air. But out of all this, just the cement alone, which is about 11%, is responsible for the main carbon emission in the whole of our concrete. That is a lot, which means the more we produce concrete, the more we use cement, the more emissions we put into the environment. And it has been proven that carbon emission is strongly related to climate change. So the cement industry itself, the way we use concrete, the way we use cement is contributing to carbon emission. So again, if we look at the various industries we have, looking at the building industry, the transportation industry, the agricultural industry, just the cement alone is responsible for 7%. I think that is huge. We might think it's just 7%, but that's actually huge. So imagine the number of industries we have, and just one industry is responsible for about 7% of the carbon emission. That is a lot. That is huge impact. Which, on a positive note, it also means if we can find a way to reduce carbon emission from the cement use and concrete production, we can really have lower impact of climate change. And people might also ask me, so I mentioned the problem is the cement. If we kind of look at how cement is produced, so the production of cement is a very complex process, but I found this image which kind of simplifies it. It shows first you get the raw material, you crush it, you mill it, then you have your clean air, then again you mill it again, then you transfer it. Looking at this, it can be seen that the main aspect where huge amount of emission and energy is used is this portion. So, as we all know, the main reason is because first, the calcination process. During the calcination of all these raw materials in the kiln, one of the products is carbon dioxide. So even there's a lot of research and development recently trying to use alternative fuels for the production of cement. Even if you're able to reduce this emission to about, let's say, 50, 80 kilograms per ton, there's still a lot of this coming out. So which means one of the ways we can really reduce the environmental impact from the use and production of cement is to use less and find alternatives. And it has been shown, I'm sure, again, this is a very popular figure I put here. We're not going to slow down on the use of cement. Again, there's a lot of construction going on. Developing countries are constructing new materials. Developed countries such as Canada and the US, we also have a lot of rehabilitation going on. So cement is still being used for various applications. Concrete is still being used, which means the more of this we produce, the more emissions we have in the environment, the more impact of climate change we will have. So it is very critical that as civil engineers, as material scientists, we kind of play our own part in improving the sustainability of the environment by looking for alternative material. So if we should look at the whole cycle or the whole life cycle of concrete structures, in fact, everything I've talked about so far here is cement. But it's always good to also know that other processes in the production and use of cement could also contribute to carbon emission. In fact, one of the recent studies we actually found recently is that the use of concrete itself could also contribute to about 10 to 25%. So it's always critical to know that not just we should not just focus on the cement production, we should also focus on other parts. But when we look again at the whole life cycle, the main emissions is coming from the raw materials and product stage. So which means again, to have a significant reduction of the environmental impact of the concrete industry, we really need to find an alternative to the conventional cement um, we use in concrete. So now, as a result of these, there's a lot of push globally now. We've heard low carbon concrete, green concrete. In fact, I know the United States have this infrastructure bill right now. They are investing a lot in low carbon concrete, green concrete. The main reason is that, again, for us to be able to reduce our carbon emission, the cement industry, the concrete industry is emitting a lot of CO2. We really need to find alternative material to use. So this has really led to development of low carbon cementitious material, and there's been a lot of studies in different areas on this, which have resulted in the use of various materials to replace cement, to the use of various technologies. So if I show the life cycle of concrete now, talking about the manufacturing stage, which is this stage, one of the ways is to use recycled aggregate or to use alternative binders such as geopolymers. Or one of the things getting common nowadays too is to use 3D printing for construction. An effective aspect for us to also reduce our emissions is effective design. Most of the time we use too much cement. So let's say recently we're taking the curve from a sidewalk and the compressive strength is 50 MPa. That is too much for a sidewalk. That is too much cement. So one of the ways for us to also reduce our emissions is to use low, and this can be achieved through effective mixture design. And also we can use various additive manufacturing, effective repair method, and so on. And I should say, to achieve a low carbon, even though in this presentation today we'll talk a lot about geopolymer, using that is not the only solution. There is need for us to use a combination of materials, combination of process to really achieve what we know as low carbon concrete. So in summary, again, we really need low carbon alternative because first, we need to really supplement the materials. So for example, even all over the world now, we have shortage of material because there's increase of urbanization. So looking for low alternative will be able to offer us a solution to this. Also, as we can see, a lot of low carbon concrete really use waste material. So this open an avenue for us to manage this waste effectively. And most times too, these low carbon alternatives are cheaper because they're using waste products. So those are the main need. So now through that, I just want to give that introduction first. Then now we'll kind of go through geopolymer and alkali activated concrete. And one thing that really separates geopolymers, alkali activated materials, from the traditional Portland cement concrete is that there's no cement. As we know, for the traditional concrete, it is made up of the Portland cement, your aggregate, which is it can be a fine aggregate and coarse aggregate, and also water. And in some cases too, you can have things like reinforcement admixture. That is the conventional concrete. The main difference between the conventional concrete and geopolymers or alkali activated concrete is the binder. So we still use normal aggregates, we still use water, we still use admixtures, we still use reinforcement, we use those fibers. But the main difference is the geopolymer binder or the alkali activated binder, which is replacing Portland cement totally. And I'd like to emphasize that this is quite different from the use of SCM. Most times when you will use SCM, supplementary cementitious material, we use them in a way that we are partially replacing cement. Whereas when we have a geopolymer or alkali activated binders, we totally replace cement. Most cases too is the same material we use as SCM, we use as precursor in geopolymer. But for geopolymer, the cement is totally replaced. And this just kind of summarizes how geopolymer concrete is produced. And as I mentioned earlier, we still use the same porous aggregates, the same water, the same reinforcement if needed. But the main difference is in the binder composition. So a geopolymer binder or an alkali activated binder is composed of two main parts, which is what we call the precursor, which is the solid precursor, or activators. The common activators we've used so far is sodium silicate, sodium hydroxide, and also for the precursors, the common one we actually use is fly ash and slag. And the reason is that these are available in large quantities. So we combine these two together to form a binder that replaces cement. Then we mix with aggregates. Then we cure. Then we have geopolymer concrete. So for a geopolymer concrete, again, the main difference is just the binder, which for a traditional concrete, the binder will be made up of just Portland cement. So if I should now kind of put a definition to a geopolymer concrete, I will say this is a sustainable alternative, even though the term is relative, it's a sustainable alternative to Portland cement. So geopolymer, the only difference again is that the binder is different. And this binder is obtained by activating various precursors, which contains aluminate and silicate monomers with alkali solutions to obtain a binder that acts like cement. And there's really a lot of, I know, a lot of confusion in this field right now. Some people use alkali activated concrete, some people use geopolymers. Even though these two are kind of similar and also they are both sustainable alternatives to Portland cement, but in a way they are kind of different. And this is based on the chemical composition. So again, I'm putting this very common figure, which I really found is really helpful, that really separates different kind of binders. So you can see this is based on the amount of calcium you have and the amount of aluminate monomer you have. So basically for Portland cement, which we have, is very high in calcium, which is responsible for a lot of the high strength we achieve, because that when you have your hydration reaction, then that form your calcium silicate hydrate, your calcium hydroxide, the heat, and so on. On the other hand, for alkali activated materials, they have a lower amount of calcium compared to Portland cement, but there's a lot of aluminum content in there. So you can see now, geopolymer itself is kind of a subset of alkali activated materials. But like I've seen a lot of these mistakes in the literature, a lot of people are actually using this term interchangeably, which should not be. Some things are being referred to as geopolymers, which are not geopolymers. But it's just good for us to have at the back of our mind that alkali activated materials cover the whole spectrum of these alternatives to totally replace cement with precursors and solid activators, whereas geopolymers is just a subset. And we can see here that for geopolymers, this has a higher amount of aluminum, but a lower amount of calcium. So, and this means that, for example, if you're using things like fly ash, especially class F, has a lower amount of calcium in it, so it falls under geopolymers. Whereas if you're using things like slag that has a high amount of calcium, we have some silicate in there, some aluminate in there, then that generally falls under the umbrella of activated materials. So that's the main difference. But for my presentation today, most of the things I'll be saying, I'll still be using those two terms interchangeably, because again, this figure I'm showing here is just a general difference. The kind of activator you use, the curing method you use could also determine whether it's a geopolymer, inorganic polymers, or also fall under other part of alkali activated materials. And I should say, geopolymers are not new. So one of the things with geopolymers is that compared to traditional Portland cement, we've not really used a lot of this material. But it's not something new. In fact, recently we tried to prepare a review that actually shows global application of geopolymers on a large scale. Even though we could not find a lot, but we were still able to see a lot of examples from each of the continents. And as we know, there's a lot of this in Australia, because Australia has really advanced in this area. And by the way, they have a lot of fly ash, so which was beneficial. So I should say again, geopolymer is not something new. It has been used for both non-structural and structural applications. So for example, this is a part of a pavement that was constructed in South Africa, and they actually use a geopolymer. And also this is a popular building we know in Australia, which was completed with the geopolymer that was made with fly ash and slag as the precursor. Also, recently in London, they were able to use geopolymer as a sustainable alternative to fill this hole. And in the US, they're actually using geopolymers for rehabilitating various tunnels, because this the use of geopolymer in this application was found to be sustainable and also was found to be cheaper compared to the traditional repair methods. So, what is the issue with geopolymers? Why are we not using a lot? Why has the progress really slowed down? Geopolymers and alkali activated materials have been around for actually a very long time. Even though it's getting more common in literature nowadays, this has been used for a very long time. So I will pinpoint, for the purpose of this presentation, we have three main issues with geopolymers. The first part is the activator we use. The most common type of activators we use in geopolymers is sodium silicate and sodium hydroxide. And the reason why we use this is because this has been proven over the years. And also this gives us a very high performance compared to alternatives. But the problem with this conventional activator is that first, it's very corrosive. Sometimes we use sodium hydroxide up to like 4 molar concentration. That is a lot. That will burn the skin. So because of this high corrosive nature of these activators, it is not practical to really use on a large scale. In fact, we can't, in some cases, use traditional concrete mixers to mix this kind of geopolymers. So that's one of the main issues with the traditional activators. But the reason why we still use this a lot is because, again, this is well known to give us the performance we want. That is performance similar to that of Portland cement concrete, or even better. Another issue with this activator is that it's very expensive. Even though we might be using a lot compared to like cement where we just add water, these activators are very expensive, which makes it impractical on a large scale. And also, the production of these are chemicals, right? So the production of this is very energy intensive. So at the end of the day, we're producing a sustainable alternative for concrete. But if our activator is already having a high embodied carbon, that will kind of remove the benefit of geopolymers. And this material is not something that is readily available. So even for my lab, if I need a sodium hydroxide or sodium silicate, I have to go through the chemical office, I have to sign some form, I have to lock it up somewhere. So it's not really practical. So that's the first issue with geopolymers. The second issue I will say is the precursors. So this is kind of less compared to the activators, but there's a huge issue with the precursors, because the traditional precursors we use in geopolymers is fly ash and slag, and sometimes metakaolin. But the issue is that, first, these materials are not readily available. In fact, currently in Canada, we don't have fly ash anymore. And that's because the government is moving towards sustainability and they are decommissioning a lot of coal plants. So which means fly ash we don't have anymore. The little fly ash we have, the cement industry is already using it for the production of cement. So we don't really have enough of this material to use. And also, even in cases where we have this material, the properties varies a lot. So I know, for example, if I should buy a cement, let's say in my province and another province within Canada, the strength will probably be the same. But if I should get fly ash or slag from two different locations, the properties of the resulting concrete will be totally different. So this is one of the major issue with the precursor. And the last part I'll really say for this presentation that has issue with geopolymer is the way we mix it. In some cases, heat curing is required. As a result of the use of heat curing for some of these geopolymers, that really makes the whole production of geopolymers very expensive. And as we know, when we use heat, we're using more energy, we have more emissions. So that's a big issue with those kind of curing methods. And also, in some cases, it's just not practical. The use of heat curing is more practical, I would say, in applications such as precast, if it's visible in those cases. But compared to the traditional concrete, we can't just use heat curing for, let's say, I'm making a rigid pavement, a road. I can't use heat curing. So that's a big issue with geopolymers. But for today, I'll just briefly talk about, because of time, I'll talk briefly about the activators and also the precursors. So one of the recent advances which has really shown promises to really advance the use of geopolymers on a large scale is the use of what we call low carbon activators. And just from the name, it means compared to the traditional activators such as sodium silicate, sodium hydroxide, these materials have a lower embodied carbon. That is, during the production, it is less energy intensive compared to the sodium silicate and sodium hydroxide. And three, so there's a lot, I think there's about five now or six that's available right now, but the ones I'm giving here is based on the example of the recent advances we've made in our lab, that the ones we're currently using. And the first one is hydrated lime, which is the calcium hydroxide, the sodium carbonate, and the sodium sulfate. All these three alternatives, first, they have low embodied carbon. In fact, most of these are found in the environment. So sodium carbonate basically occurs in the environment as natural source, same thing with sodium sulfate. Hydrated lime compared to cement is produced at the lower calcination temperature, is about, I think, 750 to 900 degrees Celsius. So all these have a lower embodied carbon compared to if we're using the traditional activators or if we're using Portland cement as the binder. And these materials basically they are so cheap. So the hydrated lime we use in our lab, basically we just go to like a hardware store, then we buy it. We don't need to sign anything, we don't have to fill anything. So these materials are very cheap. One bag of these of hydrated lime that we use is like $8. So compared to sodium silicate and sodium hydroxide, these kind of activators really open a pathway for us to develop what we call sustainable geopolymers, which can be deployed on a large scale. But there's an issue with these alternatives, which also really show that we still have to do a lot of research and development in this area. One of the main issues is low early strength. The strength at later ages is not a problem. In fact, when you use something like sodium carbonate to produce geopolymers, it has been found that it will give you approximately the same strength at 28 days compared to when you use sodium silicate and sodium hydroxide. But the problem is low early strength. So if I should make a geopolymer with sodium carbonate, at 3 days, I'll probably have like 1 MPa or 2 MPa, or even my sample is still soft. Whereas for the same mix, if I use sodium silicate and sodium hydroxide, it's probably like almost 20 MPa. So that's one of the main challenges with low carbon activators right now, which really aim for us to find ways to improve the early strength when these kind of activators are used. Also, another issue with this is that we don't really understand the mechanism. So we know over the years, we know the chemical reaction between fly ash slag and sodium silicate and sodium hydroxide. But for this sodium carbonate, sodium sulfate, and calcium hydroxide, we don't really understand it. And as we know, the construction industry is very conservative. In fact, for you to kind of make any construction, that you have to be sure of your material as an engineer, your name is going on all the documents. So you really want to be sure that the material is good. So as we don't really fully understand this mechanism, these are one of the backflip of these low carbon activators. But nevertheless, there are various ways for us to really find alternative to these traditional activators. And this could be from natural mine minerals or processed waste. So trona basically is a salt mine. Basically, we can mine sodium carbonate from trona, and also sodium sulfate also exists naturally in the environment. Other types of waste could actually be processed. So there's a lot of advances in this area. And most of this waste, especially like bottom ash, rice ash, glass waste, and so on, and silica film, these have been used to as an alternative to sodium silicate in the production of geopolymers. Whereas the industrial alkali waste, calcium carbide, and Bayer liquid were used as an alternative to the sodium hydroxide. So there's been a lot of progress in this area. I believe in the next 5 years, we should see a lot of large scale developments. There's a lot of progress really happening in Europe right now. And I believe Malaysia right now is well positioned to actually be a leader in this area to ensure like more large scale applications in this area is carried out, in addition to the laboratory verifications. And this is just an example of some of the results we got in the lab here at Windsor. So instead of using the traditional sodium silicate, sodium silicate and sodium hydroxide, all we used was that we used lime. Again, this LM is lime. Lime is readily available. Lime is cheap. It's easier to use compared to sodium silicate. It's still a corrosive material. In fact, cement itself is a corrosive material. But compared to sodium silicate and sodium hydroxide, the concentration is lower. So in this case, we made a geopolymer in which we only use slag as the precursor, and we use lime. Then the other one we use a combination of fly ash and slag at the same amount of lime. And for the third mix, we use only fly ash. So we actually found out, so this application was to improve the sustainability of ECC, which is engineered cementitious material. And as a brief explanation, ECC are kind of a fiber reinforced material, which really has a higher tensile capacity. The tensile capacity of ECC is about 100 times that of normal concrete, so it's pretty huge. So from the results, we're able to see that it's actually possible for us to produce a structural ECC using just waste products, in this case, slag and fly ash, in addition to lime. So instead of us actually producing concrete with cement or using the traditional activators, sodium silicate and sodium hydroxide, we were able to successfully produce structural grade cementitious material with the use of lime as the activator. And when we calculated the environmental impact of this, it is like about 70% lower compared to when we use traditional activators, and about 90% lower compared to when we use cement. But we can see in this case, because what we're looking for is more ideal is all these multiple cracking, we found that the combination of slag and fly ash gave us the best results. And looking at the compressive strength, you will see the more you increase the amount of fly ash, you can see LM1 has no fly ash, LM2 is 50% replacement of slag, LM3 is 100% replacement. The more we have fly ash, the lower the strength. And this really shows us in this case, lime is only suitable to use with slag. That is the only explanation. In this case, the use of lime with things like fly ash as precursor is not beneficial. In fact, at 28 days, it's still less than 10 MPa. But in cases where you're looking for all this multiple cracking, higher tensile capacity, a combination of fly ash and slag was good in this case because we're able to experience this multiple cracking. And if you can see from this graph, actually, we have a higher deflection capacity compared to when only slag was used or when only fly ash was used. So it's very critical that before all these alternative activators or precursors are used in geopolymers, we kind of have some form of lab verifications to really make sure there's good compatibility between the activator and the precursor. And also from this test, we did other tests, which is similar to the compressive strength. We found that the more we increase the amount of fly ash, the lower the porosity, which also is reasonable to be responsive for higher absorption. But then when we look at the microstructure, what we realize again is that the thesis we made earlier was correct. The lime was only able to react to the slag, and mostly because of the presence of the calcium in the slag. Whereas there's lack of really interaction, or there's lack of geopolymerization with the fly ash particles. That is, the lime we're using in this case does not have sufficient power to dissolve the silicate and aluminate monomers in fly ash. So looking at the microstructure, you can see for the one with 100% fly ash and this one with 100% slag. For the slag, this is very, very homogeneous, it's very solid, it's very densified. Whereas when we look at the one with fly ash, all these we can see there's a lot. In fact, majority of what we observe is unreacted fly ash, as you can see in this case, which also really shows that the use of lime and fly ash in this case is not suitable. And also looking at the fibers we actually put, there's no bonding between the matrix and the fibers, which shows again this in this case. So another result I'll quickly show here is another study on modern now on geopolymers, where we try to use silica film as a source of silica. So and this was against the control. So we have Portland cement, we have just in this case we have slag. So all this mixture we have slag. So slag was activated by sodium carbonate. We have glass powder was activated with sodium carbonate. We have here we have glass powder again, sodium carbonate. So I won't go too much in details into this. This shows again in this case that sodium carbonate is a promising alternative when we use things like slag as geopolymers. So we really have to really evaluate these properties before we have large scale deployments. And in terms of precursors now, so I've finished about the activator. In terms of precursors, as I mentioned earlier, fly ash and slag is not available everywhere. So I'm saying that now Canada we don't have fly ash, but in some other countries we have enough. In fact, I'm originally from Nigeria, and in Nigeria, right now we're producing, we're building more coal plants. So which means we have more fly ash. So which means in that case, it is more ideal for us to use fly ash as a precursor to produce geopolymer. It is very critical that when we produce geopolymer, that we really identify what are the locally available material. I also heard with my collaboration with Dr. Warid that in Malaysia there's a lot of Senosphere. This could be an alternative precursor in this case. So it's very critical that when we produce geopolymer, we find ways to use locally available materials as both the precursor and also the activator. But generally, looking at natural materials over the years, I have a almost 3 years collaboration now with Cameroon, where we've been able to use clay, both calcined and all calcined, to produce geopolymers. So this is a significant advancement because anywhere you go in the world, there's clay. The only problem is that the properties of clay differs. So one of the things we're trying to do now is to kind of form a classification system. If you test your clay, if you have these properties, it's class C, it's class A, it's class B, you can use it for this. But generally, one of the main advances that we have in terms of precursor over I'll say this last 10 years, is the use of clay, also volcanic ash and pumice. In terms of byproducts, one of my current research now in Canada is to explore the use of mine tailings, because Canada mines a lot of critical minerals, and we have a lot of these mine tailings just out there, posing a lot of threat to the environment. So what if we can actually use this material to produce geopolymers, to use them as precursors to produce geopolymers? But in addition to this, again, depending on location, if you have things like palm oil, fuel ash, glass waste, ceramic waste, brick waste. So ideally, once you have a waste product that has a high amount of silicate in it, aluminate, and even calcium would be perfect. All these could be used. And this has really shown the advances of precursors over the years. And this just shows a picture of one of my current research, actually, which I'm working on. These mine tailings. Ideally, these mine tailings are just put out there in tailing ponds, where basically the company spends like almost $10 million annually just to manage the tailing pond. Whereas we've been able now to turn this material into precursors to produce geopolymers, even though we still have to do a lot of tests such as leaching tests, but we've been able to advance this. So basically, initially we receive the sample like this, then we have to kind of mill them. So once we mill them, we do some activation method for us to be able to use. So I should mention again, a lot of this from the research so far, we've really found that some of these waste products might not be able to use directly, but it is possible for us to activate them or treat them and make them suitable as precursors in geopolymers. And this just shows some of the initial control we did. And this is not actually geopolymer. So this is just like control, where we actually use these mine tailings to replace cement. So this is just as SCM replacement. And we can see as long as you still get to about 25 replacement of cement, they're still good performance. And also the use of things like silica fume along with the SF. So by the time we use silica fume in this case, along with the mine tailings at 25% to replace this, there's an increase in the strength. So again, when we use these alternative precursors, there might be need for us to also use some traditional material to replace them. So if I'm using mine tailing, I might have to mix like maybe 5% of slag, 10% of slag to achieve the desired strength. And this just shows the picture of the testing. And because of the color right now, that's why we do a lot of leaching tests, because these mine tailings have heavy metals. So right now we're really testing to ensure that this material, these heavy metals, does not leach into the environment. So hopefully we're able to figure that out soon. But generally, based on review that was carried out this year, it has been found that if there's a waste product available locally in large quantities like xenosphere, mine tailings, clay, volcanic ash, if they have a high amount of silicate with calcium or even some aluminates, they are very ideal for precursors in geopolymers. So this figure is only talking mostly about mine tailings, and basically I was able to find mine tailings from various sources and their chemical composition. So it can be seen here that the main part that plays a role in this reaction is the silicate. So once you have some silicates, then if you have some calcium or even some aluminates, then you can really process that material as a precursor in geopolymers. But as I mentioned, ideally too, we can't really use these raw materials like that. Most times, especially if you're using an industrial waste product, you might really have to process them. And again, these advances over the years have really shown us that even though we can't use this in the current state, just minimal processing, not too much processing, minimal processing, we could really transform this waste into cement replacement. That is, you can end up using this material to totally replace cement in the production of geopolymers. And one of the ways to really do this is through what we call alkali activation. So I should mention, this is different from the geopolymer binder itself. So this is before you mix your concrete. So when you obtain your raw material, you kind of add like a little bit of alkali, then you mix it together, then you dry it. So that's called the alkali activation of mine tailings. And also, there could be various ways to really achieve this. It could be through mechanical, and this could be just through you grinding your waste products to reduce the size, to increase the surface area, and they become more reactive. And also, it could be through chemical reaction in which you use various chemicals to achieve new phases. And one tool that we find that it has been really helpful nowadays is that we use thermal activation. So this is also similar to calcination of clay. So basically, these mine tailings, we subject them to about 100 degrees Celsius, and we're able to find them to be more reactive in this case. So generally, any waste product, any solid waste products available in large quantities could be explored. But the main thing is to check first their chemical composition, whether they have sufficient amount of silicates, aluminates, and some calcium will be great. And these are just some of the results from the activation method. In this case, they actually found that grinding, just initially, if you have a mine tailing, just grinding it alone for 5 hours increase the content of the active silicate and aluminates and makes them suitable to be used as precursor in geopolymers. And also in this case, it was found that like using just initial alkali just to cover the precursors resulted in, you can see the deterioration of all these peaks, which means in this case, we have more amorphous phase compared to this one. So this treatment could be done with minimal energy. It's not energy intensive. And at the end of the day, because we're replacing cement totally, this is still very sustainable. With all these advances so far in terms of the use of the alternative precursors, the use of alternative activators, there's still a lot of challenges. In fact, as I said, That's one of the reasons why we're not really using this on a large scale. But this area is very promising, and we expect a lot of changes, a lot of advancement, more advancement to occur in the next 5 to 10 years. And one of the main issue is that there is lack of standard or guidelines for the mixture design or even structural design. We've been used concrete, traditional concrete over a long period of time. There's a lot of standard, ASTM standard, Malaysian standard, ACI standard, CSA standard. But this standard, there is none that really exists for geopolymers. So which means even if you have a good geopolymer performing very well, there's no way an engineer can use it because there's no guideline that really supports its application for in terms of the mixture design itself or even for structural application. And this is one of the reasons why we have to ensure that our standards are moving more towards performance-based standard rather than prescriptive-based standard. Another major issue, which I actually mentioned earlier, is the inconsistent characteristics of the precursors. Even right now that we use a lot of fly ash and slag to produce geopolymers, if you obtain your slag or fly ash from two different sources, it will give you two different properties, which is the main challenge. So there's really a call for us to really find more way to classify this. So for example, for cement, we have type 1 cement, type 2 cement, type 3 cement. If we can have those classification for those precursors, that will really limit this challenge with the use of these alternative materials. And also there's still a lot of issues with fresh and durability issues in terms of fresh, especially when you're using things like silica film and slag, it has lower workability. And in some cases, if you're using like slag to produce geopolymers, it has a lot of issues with sulfate attack, which this has to be resolved. So we're hoping in the next couple of years, in the 5 years, hopefully, we're able to resolve this issue. And one of the other thing is that which is very common nowadays and which people don't actually believe geopolymer is that people are calculating the embodied carbon or they are doing the LCA differently. It is possible to produce a geopolymer that is not sustainable, especially when you're using heat curing or if you're using all these high embodied activators or you have to ship your precursor over the country. So there is need for us to also have a general method, and this also goes into the standard and guideline. If we can really have a general way to really quantify the embodied carbon of geopolymers, this will really make people also accept this material more in the industry. And also another issue is the environmental implication. As we know, even though we have fly ash itself, the production is very bad for the environment. The production of power from coal is bad for the environment. And that's why Canada has decommissioned its coal plant. But in places where it is being produced, there's still a lot of issues with the production of the fly ash. And also another big issue is that there's a lack of large-scale deployment. Over the years, there's been a lot of research in the lab in this area, but there's really lack of large-scale development. As I said, we try to find global examples of geopolymers, that is, where geopolymers was actually used for a real structure, for a large-scale application. We could not even find up to 20, even though we're able to find one each from each continent, but we could not find up to 20. And majority of the ones we found too are also in Australia. So I think there is need for us to have more pilot study in this area in order to propel the use of these geopolymers as a sustainable alternative. But again, this field is very promising, and the future research in this area should focus more on optimization of the mixtures in order to have more consistent properties. And also, a key part of these would be to use materials available locally. Because there's fly ash available in a particular part of the country or in a particular country does not mean we should use that same everywhere. So let's say, for example, if I'm making geopolymer for large scale application in Malaysia, one of the key things I'll do first is to see what material is available on a large scale that we can use. Then I can engineer those material, activate those material, and use them to produce geopolymer. Because when you do that, you're managing the waste and also you're reducing the embodied carbon because you don't have to transport those raw materials. Also, there's need for more research in the future to really focus on durability and long-term performance. A lot of the current studies, a lot of the applications we have right now, the only thing they mostly test is the mechanical properties. But as we know, mechanical properties is not sufficient for concrete materials. We need to see the durability in various environments. Can I use this material in a cold area? Can I use it when the weather is hot? Can I use it for the construction of a bridge press? So we really have to explore this. And also, I should say, geopolymers AM, we should not really see it as a total replacement of cement or total replacement of traditional concrete. We're better off starting using geopolymers for specialized application. So we can say, if you want to make sidewalks, yes, use geopolymers. If you want to make lightweight concrete, use geopolymers. So we should not really see geopolymers as the all-around solution for, if in fact, it can be the all-around solution for traditional concrete at this stage. So one of the ways we could really advance the application of geopolymers is to kind of create them for specialized applications, and this will also improve its acceptance in the industry. So I'll just kind of summarize here, and Professor Wade will continue more on this, is that cementitious materials such as concrete, this plays a critical role in sustainable development. It doesn't matter the part of the world we are, the country we are, concrete is very essential. We use this material for the construction of our infrastructures. And again, because of the properties, we can use it for the construction of various infrastructures, both structural and non-structural. However, geopolymers and alkali activated materials could be a sustainable alternative to this material. In fact, these geopolymers should not replace traditional, but could supplement traditional concrete. So instead of us using the traditional concrete for all applications, as I mentioned, we can have geopolymers just for specialized applications. So this kind of balance out at the end of the day. Another thing that is critical is that when we're evaluating sustainability of concrete in general and geopolymers, there is really a need for us to incorporate the performance. It does not make any sense, for example, let's say I develop a geopolymer, then instead of achieving 50 MPa, if a traditional concrete is 50 MPa, then I develop a geopolymer that has, like, let's say 25 MPa or that has lower durability. Then in that case, it's not really sustainable. So when we talk about sustainability, it is critical that we also compare to the life cycle, to the lifespan, to the performance of the material before we say a geopolymer is sustainable. A huge thing that will really propel the application of geopolymer forward is for us to really find ways to use these on a large scale. And when I say large scale, we don't really have to go construct a bridge with it. But let's say even in Malaysia, on a campus, on a street, we can just make a small sidewalk and monitor this over the years and see the performance. These will be an examples to show engineer that this material can perform very well. And this will be the end of my short presentation today. I tried to make it brief. If you have any question pertaining to geopolymers, alkali materials, I'll be happy to answer. And thank you so much, everybody, for attending this session and for listening. Thank you so much.
Thank you very much, Professor Adeyemi. Thank you for the insightful invite now, Dr. Warid. Okay, before the speech, I would like to take this opportunity to introduce Dr. Warid as well. Okay, Dr. Warid is an accomplished researcher with expertise in several critical areas. His focus includes geopolymer concrete and advanced construction materials. Additionally, he excels in material construction and building materials, as well as repair and rehabilitation. His impressive Google Scholar with H Index 12 and Scopus H Index 12 underscore his significant contribution to Ringgit Malaysia, and his expertise extends to consultation, making him a valuable asset in advancing research and practical applications. So, without further ado, Dr. Warid, the floor is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning, everyone. So, thank you, moderator, for the warm welcoming, and thank you also for all the effort that has been made by the JET firm together with the collaboration with the Unicel in order to make sure that our webinar is successful, inshallah. So, I also would like to express my sincere appreciation to all the participants. I think the background from the participant is civil engineers, we have consultants, contractors, and we have also professors, Dr. Andre, and also students. Thank you for your active engagement and eagerness to learn and share that has been made in this webinar. And okay, so let's start our webinar. Let's continue our webinar. All right. So I think I have already shared my slide. Everybody see my slide now?
Yes, doctor, it's there. Thank you.
Okay. All right. Okay. Thank you so much. So all right. So welcome everyone to our today's webinar. So this is our first webinar for 2024. Entitled Recent Advancement on the Geopolymer and Lightweight Concrete, organized by Jet Firm Consultancy Sdn Bhd. So I think Prof. Dr. Adeyemi from the first speaker has extensively covered the topics of the geopolymer in his recent presentation. I just would like to continue a little bit on the discussion and maybe some works that has been done in Malaysia, which focusing on the geopolymer to be used as a repair materials, and also some knowledge and some experience on the lightweight concrete. I mean, we focusing on the geopolymer lightweight concrete. Okay, so without further ado, as you can see in my slide, there is a picture where the University of Queensland Global Change Institute, designed by Hassel in conjunction with the Blight Tanner and Wegness, where this is the world's first building where successfully used geopolymer concrete for the structural purposes. I think this is about 4-story high building that has been used for the general public, where comprises of the 3 suspended geopolymer concrete. So meaning that this geopolymer concrete is actually has been successfully being used and also applied in the construction industry. And someone raised a hand. Do you have any questions? Li Hyang. Okay. Mr. Li Hyang. Yeah, you can interrupt while I'm giving the presentation, no problem. So maybe moderator can open the speaker
On the mic. Okay.
on the mic. Yeah.
All right. Okay, sure.
Yes, Mr. Lee.
I think he accidentally pressed, doctor.
Oh, okay. All right. Oh, it's okay. So let me continue. Yeah, so it's okay. If you have any questions, feel free to interrupt me at any time. No problem. Okay. Okay. So yeah, ladies and gentlemen, I think before we start, let me change my slide. Okay. I have one video. I think because we are all know that to start for my sharing section, I would like to start with this video. This video is does not related to geopolymer or the lightweight concrete, but it is like some reminder or the lesson that we can learn together, especially for the student lah. All right. So this video is actually related to the priorities. Okay. If you can see, there is a container or a jug that has been filled by the various items. The professor, they put golf balls, and then the pebbles, and then the sand. Okay, so yeah, start filling the jug with all these materials. So what I would like to share here is about the priorities, because nowadays I see that most of our students and most of us are not aware or not does not really know the importance of the priorities. Okay. Yeah, just can you imagine if you start filling that jug or that container with the sand? So the golf ball, you will soon find there is no room left for the larger items, right? But when you put the golf ball first, and then after that the sand, so that the container has been filled up with all this material. So meaning that when you are properly, or you plan very well your task and everything, you know how to begin your day with the important things, then you can manage, and you can achieve many things in a day. All right. So just this is just like a metaphor, which illustrate the importance of the prioritizing our tasks and commitments. So by focusing first on the most important and important tasks, we can assure that our container, which represent our life and our time, is filled not just with the activities, but with the meaningful action that reflect our true priorities, our main important things and values. Okay, so let's start our webinar. So of course, we need to have a target. Okay, so we start our webinar with the outcomes as highlighted in my slide. So what are the priorities for today's lesson? Because if you want to talk about the geopolymer, we want to talk about the concrete, we want to talk about the lightweight materials, there are so many things. There are so many knowledge and so many experience, so many lessons related to this topic. But what is the main focus for today's webinar? The first one, we need to be able to, identify what are the problems with the when we utilize the special concrete. I think Prof. Dr. Ademi also highlight the issues and the obstacle that has been faced by the researcher, by the practice contractor, and etc. So after we identify the problem, so what is the solution? Every problem has the solution. Saya punya cikgu, dia cakap ada dua je yang tak ada solution. Satu mati, satu tua. Kan? Selain daripada death and your age, ada solutionnya. Alright? So what are the solution by considering the safety and environmental consideration? And the last, I will share also the mixed design and some introduction and background of the lightweight concrete and how to produce the lightweight by considering the density and also the strength and of course the performance of the lightweight concrete. Okay, so yeah, of course, this is the issue. Okay, this is the global issue. So what is really happening in the world today, especially in the cement industry, as aforementioned also by the Prof. Ademi, in Canada, in US, and I think also in Malaysia. So we have the same problem, which is about the carbon emission to the environment. Because one of the pollution created by the cement industry is smoke. This smoke contains carbon dioxide. Because the production of the cement, they required a burning process. And yeah, of course, if you can see all the construction structure or the construction material that available that has been practiced nowadays is made of concrete. Most of our infrastructure, bridge, building, our house, our building, work building, and etc. So the cement sector is the third largest industrial sources of the pollution by emitting more than 500,000 tons per year of sulfur dioxide, nitrogen oxide, and also the carbon monoxide. And I think with all these problems and the pollution, it creates a global problem that affects significantly to our environment. And if you can see the data from the cement industry, okay, so it contributes a lot to the global warming issue. And yeah, from the China manufacturing process, it kept increasing until 2017. And the China producing almost 4,000 million tons of cement because it is the largest country in Asia. And Malaysia not in the list that promoting this, but we need to find the alternative. So what are the alternative for this cement? We know that the cement, especially the Portland cement and what other types of the cement, is a good binder, but we need to figure out and find the alternative in order to create a new kind of the binder, a new kind of the cement, a new kind of the material that can be used in the construction industry. As aforementioned by the Prof. Ademi, in Canada, they have a lot of the red mud, the bauxite, if I'm not mistaken. So yeah, in Malaysia also we have a lot of waste that has very high potential to be used as a cement replacement, and also can be used as the new cement. All right. And so instead of we are solely depends on the our bukit, okay, our bukit limestone rock and etc. So we need to find an alternative by utilizing this recycled waste. So as you can see, when we design or choosing the materials or any technology, we have to consider the impact in terms of the cost, in terms of the environment, in terms of the society. So just now, Prof. Dr. Ademi also highlight when we are going to develop this new kind of the cement called geopolymer, they required a cloud activator. So when we are talking about this cloud activator, it's about the cost. So we try to find the alternative for this cloud activator as well. So instead of the cement itself, we don't want to create a new we don't want to create a new problems that we think that is the solution for the cement. You know, kita cuba nak solve the problem, but kita tak perasan at the same time we also create a new problems. Macam tu kan. So we try our best to have a new kind of the cement because of the adverse effect from the production of the OPC. So I think most of you are aware on this cement production. This is overview of the cement plant. So what is really happened in the cement plant? This is just some overview of the production process of the cement in Malaysia. Actually, we need to burn around 1,000 to 1,500 degrees Celsius, which release significant numbers of the CO2 to the environment, because we need to burn this calcium carbonate in order to produce the calcium. Okay, because we need that calcium for the hydration process. And this led to the global warming, and it involved imbalance in the environment. And of course, the ozone layer will affect our environment, or the air pollution, and etc. But of course, the pollution or the effect of this the factor that affecting the environmental pollution is not only coming from the cement industry, but it's also come from other industry like vehicles and etc. But still, the demand of the OPC is keep increasing by the years, and you can imagine in 2050, if we are not thinking about the alternative to this binder, maybe we are living and we need to everyone need to wear, like during COVID, right? We need to wear all the masks. Maybe in the future we need to wear uh, helmet with the oxygen. Okay, because our air is rich with the calcium dioxide and other gases that may be harm to our environment. So mitigating those emission and the problem associated with these problems, a new type of the alternative sustainable green and environmental friendly material, so-called geopolymer, is realized. Okay, so let me give some introduction. Bila saya buat pembacaan on this new cement, which is so-called geopolymer, we also find the other name. Nanti kalau kita baca, we Google this new types of the cement, ada banyak kata apa, nama yang diberi, but it's actually it's a zero cement, right? We are not using the cement at all. So for example, eco cement, green cement, like just now Prof Ademi highlight about clay activated materials. Okay, so this is the other names of the geopolymer. In organic polymer, sometimes they call it as an inorganic polymer, and sometimes they call it as a eco polymer. Sometimes they call it as other types of the green concrete and etc. So what are the difference between them? So the first is about the geopolymer. Okay, so like a conventional concrete, we will use OPC mixed with the water. So that is the material that we use for the production of the Portland cement concrete, right? And for the geopolymer, it's actually the same things, but we replace the cement with the waste like fly ash, slag, kaolin, metakaolin, and other source material that contain high silica and alumina. And we need to combine with the clay activator, which is will act as like a water. You know, if cement, we add with the water, but in the geopolymer, we add the clay activator to the fly ash or the slag, and it will form a binder and does not use any Portland cement lah. So because of the chemical reaction that takes place in the polymerization process, so the material is so-called geopolymer, right? And in Malaysia, we have a variety of the raw materials that waste materials that can be used as the precursor of the or the clay activated materials for the geopolymer. Okay, and yeah, it's the same when we talk about the eco cement. It also does not involve or does not use any cement. It utilize 100% this waste and no cement at all, no addition of the cement. So it will cut costs and everything. And sometimes they also call it as a green cement. Why green? Because the green itself reflect to the utilization of the waste from the industry. For example, the fly ash is a waste from the coal combustion process. Kalau kita tahu kita punya apa nama electric generation yang dekat Malaysia ni, for example dekat Kapar Energy Venture dekat Klang, and also kita ada a few apa nama kita panggil power generation punya electric power plant dekat Manjung kita ada. Sebab kita generate elektrik dekat Malaysia ni menggunakan one of the source elektrik ni kita bakar, kita burn our coal, okay, kita burn arang. Arang tu pun kita ambil daripada luar negara jugalah. So kita bakar dia and then daripada tenaga haba tu dia convert jadi tenaga elektrik lah. And then bila kita bakar dia akan hasilkan waste. Kalau you can imagine kita bakar sampah kan, perasan kan kalau kita bakar sampah, nanti kita nampak ada like something ash yang akan terbang naik. Itu fly ash yang saya masukkan tadi tu from the coal combustion or from the power plant industry ni. And kita juga ada waste from the agriculture. Kalau tengok dekat Malaysia ni kita banyak penanaman apa nama padi, kelapa sawit, itu yang dua yang main lah. So kalau awak boleh Google dan you all boleh baca, memang dah banyak dah researcher menggunakan this so-called rice husk ash, okay, digunakan juga sebagai cement replacement, and also in the geopolymer digunakan juga sebagai precursor ataupun aluminium silicate source material untuk replace our cement 100% ni tadi. And daripada kita punya palm oil, we call it as a POFA, palm oil full ash. Dia mesti bentuk macam powder lah sebab kita nak replace cement. Tetapi ada juga yang bentuk dia macam aggregate, macam palm oil clinker. Okay, yang itu kita akan replace aggregate lah. So banyak benda. Tapi hari ini kita bercerita tentang cement lah. Alright. Because the production of the concrete, we need a cement. Cement ni akan act as a binder. Kalau kita compare dengan aggregate, sebab kita bila nak produce concrete kan, we need to have a cement, aggregate and water. Tetapi yang the main issue kat sini adalah cement itself lah. Okay. Dan kita fokus kepada cement. So we use all these materials like fly ash, slag, kaolin, rice husk ash due to the properties is quite similar to the OPC. I mean that the similar in terms of the physical properties and certain chemical composition that required hydration process. Bila kita kata hydration process ni bermaksud simen campur dengan air tu dia akan mengeras. So proses pengerasan tu adalah hydration process. Itu dia punya conventional concrete yang digunakan sampai hari ni itulah. Kalau geopolymer yang saya kata tadi fly ash campur activator tu dia akan harden through geopolymerization process. Okay. So so this bring geopolymer claim as green and the most kita kata the most sustainable construction materials and alternative construction materials yang kita adalah setakat hari ini. Okay. Alright. So I think this has been explained by the Prof. Adeyemi. So kat sini Portland cement base tu itu yang kita banyak guna dekat conventional punya concrete. Okay, so dia tinggi kalsium. Kalsium ni yang kata kita dapat daripada limestone yang kita bakar tadi tu, right? Yang kata release CO2 tadi tu sebab dia memang perlukan kalsium untuk dapatkan C3S, C2S, C4AF dengan C3A dalam cement punya composition tu, dalam OPC cement punya composition. Tetapi dalam geopolymer we does not required calcium. Okay, as long as we have silica and alumina in our precursor, in our aluminum silicate source material, so we can activate this silica and alumina to become the geopolymer. Tetapi ada juga source material ataupun waste material yang tinggi kalsium. Macam tadi Prof. Adeyemi explain ataupun sharing berkaitan dengan lime dan juga slag. Slag contain very high calcium, macam cement. Okay, so that dia kita categorize this cement as apa kita panggil dia sebagai alkali activated materials. Okay, so there is so in a summary, both geopolymer ke alkali activated materials both are eco-friendly and it is an alternative to the Portland cement and involve the use of the alkali activator to initiate the chemical reaction. All right, and different precursor materials will have a different mechanism. All right, different chemical reaction, especially for the high calcium and low calcium geopolymer system, and also will resulting a different microstructure of the geopolymer itself. All right, so yeah, we can say that geopolymer has a more specific aluminum silicate precursor and polymeric structure, where the alkali activated material can be made from the broader range of the precursor and result in the variety of the structure for the concrete. Okay, so this is the difference between the OPC and also the geopolymer. Okay, so as we can see that the conventional concrete, right, we are using cement, and kalau you boleh tengok sekarang ni dekat pasaran pun kita dah ada blended cement ataupun kita call it as a composite cement. Kalau boleh tengok, itu adalah campuran antara ordinary Portland cement and fly ash, okay, ataupun ada pozzolanic material. Tetapi in the geopolymer we didn't use cement at all. Right, we only depend on this fly ash or metakaolin or slag as our precursor. Sometimes we use one precursor. Sometimes we use more than one precursor. We call it as binary geopolymer, tertiary geopolymer. So binary meaning that we combine two precursor, for example, fly ash and slag. So that one is a binary. Tertiary, we combine three precursor. We combine fly ash, slag, and kaolin. All right. So different application, different formulation, and different mixed design. Okay. Okay, so this is the some background or the knowledge related to the OPC. And yeah, OPC will harden through the hydration process and we will cure in the water. Kalau awak tengok construction kan kita perlu, kalau dulu dekat dalam kelas kita perlu rendam konkrit OPC. OPC konkrit tu dalam bathtub kan sampai 28 hari. Sebab kita nak pastikan dia hydration process tu berlaku dengan sempurna lah. While geopolymer is the combination of the precursor and the cultivator, and it does not harden through hydration. We call it as a geopolymerization process. Alright, so the geopolymerization process will produce two main binder gel lah, normally Cash and Nash. Alright. And kalau OPC cement ni yang mix with the fly ash and cement ni, dia akan produce calcium silicate hydrate and calcium hydroxide. The rest yang lain sama. Kalau kata the rest tu maksud saya when we want to produce the concrete, we need to add coarse aggregate and fine aggregate. Itu sama. The difference is the binder itself. Binder tu bermaksud pengikat yang kita guna dalam konkrit tu. Alright. Kalau kita tengok dua-dua ni, dua-dua menggunakan fine aggregate and coarse aggregate like a gravel and sand dalam production of the concrete tu. Tetapi the difference is the binder itself. Satu ada cement, satu without cement. Okay. So there is okay, ini my mixed design yang saya buat during my PhD. Alright. Okay, so based on this mixed design, okay, I can say that kita punya starting research kita tu, kita mesti characterize the raw materials tu dululah. Alright, meaning that kalau kita ada waste daripada mana-mana yang kita tengok high potential, kita nak tahu dia berpotensi ataupun tak, the first thing first kita akan buat characterization dahulu. Alright, characterization ni meaning that kita akan tengok chemical composition. Dia ada tak silika, dia ada tak apa nama alumina yang kita nak lah dalam kita punya precursor tadi tu. Okay, and then bila kita dah tengok ada, and then kita check juga itu kita menggunakan XRF, X-ray fluorescence. And then kita akan check juga dia punya microstructure using SEM dan juga phase menggunakan XRD. Kemudian kita akan prepare a clay activator yang kata tadi act as a water dalam conventional concrete. In polymer kita kena prepare the clay activator. Clay activator ni yang dalam saya punya research saya menggunakan sodium silicate and sodium hydroxide. So the combination of this raw material like a fly ash and the clay activator, kita akan produce paste, and then we will add with the aggregate in order to produce the mortar. Sebab saya buat repair materials, okay. So bila kita produce repair material ni, sometimes kita punya structure tu dia spalling ataupun dia crack. Kalau crack, kita gunakan paste lah sebab dia halus kan, crack dia kita kena grout masuk. So grout tu normally saya akan guna paste, and untuk spalling kita akan menggunakan geopolymer mortar. Alright. So this is the basic ingredient yang saya guna dalam basic process in order to produce the geopolymer for the repair purposes. Alright. But again, bila tak kisahlah what kind of the concrete yang kita buat dan sebagainya, kalau kita sebagai engineer dan sebagai contractor pun, kita nak produce concrete that will achieve adequate workability, can achieve adequate strength, and also can achieve adequate durability. Okay, so that is the three benda penting lah when we are talking about this formulation. Okay, so this is banyak precursor yang boleh guna untuk dijadikan sebagai cement replacement. Okay. And kalau kita boleh tengok dekat sini, we have construction and demolition waste. Kan, kalau kita tengok waste daripada slag. Slag ni adalah daripada kilang steel. Alright. Steel production. Sekarang bila kita potong besi kan, dia ada waste dan sebagainya. Dan also daripada molten slag tu, kita boleh gunakan dia sebagai precursor juga. Okay. So yeah, we have a few that available in Malaysia, and also certain ni dia dah guna dah dekat industri. Bukan kita talking about this research, tapi industri dah successfully guna lah. Alright. Tetapi yulah, each precursor they have their own properties. Nak fahamkan semua precursor ni, I think banyaklah benda yang kita nak tahu kan. Cumanya kita faham what is the roles, what is the main ingredient dalam geopolymer tu sendiri. So let's say kalau kawan-kawan dekat industri, you have all these waste dan you rasa nak recycle, nak gunakan dia sebagai concrete binder, you can come and see me ataupun other researcher lah. So we will try to provide best formulation. Kalau kita tak boleh buat geopolymer pun, kita boleh replace certain proportion of the Portland cement pun, that would be okay dah. Sebab kat situ pun cut cost dan sebagainya. Okay. So yeah, in order to determine the suitable precursor, kita kena identify the best chemical composition lah of our source materials tu. Okay. And okay, alright. We have a clay, slag, red mud. Tadi yang Prof Ademi guna tu red mud. Sebab dekat Canada banyak red mud. Okay, so kita ada klasik, fly F. Kalau Indonesia, dia orang ada pseudo mud. Dia ada mud ni lepas berlaku letusan gunung berapi tu, dia akan produce this waste. Itu pun kita tengok ada potential untuk digunakan sebagai raw material. So ini yang saya masukkan tadi. Kita panggil X-ray fluorescence untuk kita dapatkan the chemical composition of the fly ash. Ini kita ada alat ni dekat UiTM dan juga dekat Unicell pun kita ada. So kalau mana-mana industri yang nak check the composition of the waste yang ada dekat industri tu, you can come and see us lah. So dekat sini kita akan check dia punya silica content, alumina content and iron content. And one more is the calcium content. So this is the 4 chemical content yang very important untuk kita check before we can try to proceed with the next step lah, which is formulation. So this is the clay activator yang digunakan, tetapi macam Prof tadi cakap, dia agak cost dan we have alternative daripada sini. Okay, and this is yang available dekat lab. Kita ada kaolin, slag, rust and fly. Kalau ada industri yang berminat nak produce your own product, kita boleh buat juga. Kalau you nak repair materials ke, you nak buat packaging, you nak jual repair material, ataupun you nak jual macam baru ni saya pergi kedai hardware, dia ada 3-in-1 cement tu kan. Kalau kita nak guna untuk render ke apa benda tu kan, kalau you sendiri yang nak produk tu, then we can do for you, no problem. Kita boleh buat the formulation untuk orang kata industri yang berminat lah. So this is some properties. Kita boleh achieve sampai 100 megapascal. Okay, it depend on the formulation, it depend on the mix design yang kita guna. Yang ini nanti kita mix design ni nanti saya akan ajar detail dalam training yang akan kita buat after this. So siapa yang berminat untuk belajar nak buat mix design ataupun nak buat produk sendiri on the cement ataupun concrete product tu, macam contoh dia nak kata dia nak berminat nak buat saya nak buat waterproof punya concrete lah, doktor. Okay, you come and see me, kita boleh discuss sekali dengan Jet Firm punya consultancy. Alright, so kita tengoklah macam mana kita punya step by step yang kita nak kena buat tu. Okay, so we have right now kita ada formulation for the geopolymer repair materials, and kita ada formulation for the soil stabilization. Okay, okay, this is Kalau awak tengok kan, ini saya terjumpa video ni kan, very simple. You tengok dia repair potholes yang ada dekat atas jalan, gitu je. So I assume this is the product yang dia guna lah, which is the geopolymer kan. Dia letak, kalau you tengok dia letak apa nama, kita punya clay activator, and then kita put our fly ash mix with the sand, and then kita spray kita punya clay activator sekali lagi, and it completely hardened. Alright. Okay, so this is some microstructure. I think yang ni tak berapa nak berminat sangat kot nak dengar kan. Dia lebih kepada kita zoom ke dalam, macam tengok apa nama COVID kan. Kita zoom masuk tengok apa the shape, what are the physical appearance and the reaction take place after certain duration ataupun certain kata apa mechanism yang involve bila kita utilize new waste materials dalam kita punya geopolymer production tu tadi. Okay. So saya pun tak ni banyak dekat sini, and kalau you boleh tahu tentang microstructure ni, normally kita target kita nak reduce the porosity of the concrete. Sebab kalau concrete tu high porous, bermaksud kata apa, water ataupun udara boleh penetrate dekat kita punya concrete, and it will reduce the strength and the durability of the concrete. Okay, so kalau you boleh tengok dekat microstructure image ni, ini kita dapat daripada scanning electron microscope. Ini pun ada juga dekat UiTM dan juga Unicel. Alright. Unicel I'm not sure, tetapi UiTM ada. Kalau nak buat you can contact. Kita nak tengok structure. Yang tadi kita kata bila kita dah ada waste materials, kita mix with the clay activator, and then dia akan produce cash and next. So daripada sini kita akan monitor pembentukan cash dengan next tu tadi. Sebab itu very important. Kita tak naklah dia keras tapi tak kuat. Kan? Dia harden tapi dia tak boleh bagi kat kita strength dengan durability tu. So kita tak mau macam tu. Alright, sebab we have different types of the precursor. Tadi yang saya list tu ada lebih kurang 10 kan. Macam-macam precursor. So kita kena monitor dia punya microstructure development dia. Okay. Alright, so untuk geopolymer repair materials, normally kita akan menggunakan high calcium fly ash. Ini kita boleh kategorikan dia sebagai clay activated materials lah. Alright, and kita kena optimize dia punya solid to liquid ratio, sodium hydroxide molarity, etc. Sebab kalau too high dosage of the sodium hydroxide ataupun molarity too high, it may corrode the reinforcement. Sebab kita kadang structure kita ada reinforcement kan dalam tu kan. Kalau RC, concrete dan sebagainya, so we need to optimize all these things. Alright. And kalau terlalu banyak sodium hydroxide and sodium silicate pun dia akan menyebabkan coasting. So it's okay. For those yang who need further clarification or further information related to the formulation, you can contact or just email lah to us and we try to help. So this is some microstructure yang kita ada. So this is other application based on the silica to alumina ratio. Because the silica to alumina ratio ni in geopolymer plays crucial roles in determining their properties and consequently their potential application. Kalau kita boleh tengok kat sini, formulation yang saya buat dengan team saya, kita akan based on the silica to alumina ratio. So because this SR2R ratio will reflect to the potential application of the geopolymer. Ini yang dikeluarkan oleh Institute of the Geopolymer, where they study how variation of this ratio can affect the physical and mechanical properties, and they try to fit what are the best or suitable application for the geopolymer. If you can see, when the silica to alumina ratio is getting low, the resulting geopolymer metric tends to be more aluminous, and which can lead to a material with the high mechanical strength but low chemical stability in aggressive environment. So yeah, it's often suitable for the structural application where the high strength is critical, but they may not perform as well in acidic environment. So kat situ bila we are talking about the environment yang beracid dan beralkali dan sebagainya, so we need to adjust the silica to alumina ratio. Alright. As the silica to alumina ratio to increase, the geopolymer matrix pun akan become more siliceous, right? This typically will improve the chemical resistance and durability and making this material ideal for the application in aggressive chemical environment. For example, waste encapsulation, chemical containment, and lining of the sewers and pipes that might be exposed to acidic or corrosive substances. However, too high silica content can lead to the more brittle, right? So we need to optimize the content of the silica, right? Because it might reduce the structural applicability of the geopolymer. So optimization of the silica alumina ni nanti kita akan buat training. Sebab benda tu kita kena buat physical. Saya kena ajar you manual, kita ada borang, kita punya mix design form yang kita kena guna. Macam kita buat mix design konkret kan, kita menggunakan apa nama form yang daripada BS tu kan. Dia lebih kurang macam tu. Saya ada create borang saya sendiri untuk buat mix design for the geopolymer ni. Right? So an optimal range of the silica to alumina ratio ni is often sought to balance these properties lah, aiming to achieve a material that is both strong and enough for the structural use and durable enough for the long-term exposure to the harsh environment and as well, right? So yeah, we can tailor wide range of the application, precast concrete product, nak jadikan the panel, beam ataupun repair material for the infrastructures yang saya dah buat masa PhD saya tu, and heat resistant ceramic and etc. Alright, so it's important to note that the specific application of the geopolymer based on their silica to alumina ratio that can be influenced by other factors such as type of the precursor, applied to the composition, curing condition, and the presence of the additional additive or filler. Itu ni lah. Right? And a few companies yang dah buat, kalau awak tengok dekat Louisiana, dekat US ni, Alchemy Geopolymer Solution, specializing in the geopolymer technology. Alright, it provides environmental friendly solution for the infrastructure repair and construction. And their product are designed to be durable, to reduce carbon footprint and resist harsh chemical environment, making them suitable for the wide range of application. Dekat Malaysia belum ada lagi company yang buat geopolymer ni, right? Kalau kat luar banyak lah, Wagner Global, Zeobond, Ceramatec, Banah UK dan sebagainya. Alright, so all these companies are at the forefront of the geopolymer technology, where they're driving innovation and sustainability in the construction industry. So their success story kita boleh rujuk dan kita boleh tengok where underline the potential of the geopolymer to replace the traditional building material in the wide array of the application, paving the way forward greener and more sustainable and more durable infrastructure. Alright. Okay, so this is a few company. Ada yang buat packaging macam bag cement pun ada. So kalau ada company kat Malaysia yang berminat, you can come and see us jugalah. Alright, this is in Melbourne, Zeobond. Okay, I think saya pun tak nak kata apa. This one kita saya tak nak pergi dalam sangat lah. Okay, so this is all the finding masa saya punya PhD dulu. Right, optimum binder to cell ratio 1:2, and we can achieve the compressive strength up to 50 megapascal within 1 day. Alright, sebab kita nak repair, sebab saya buat untuk repair jalan. Okay, bila repair pothole jalan ni yang rigid pavement lah, yang dia punya substrate tu adalah concrete, we need a very fast setting and high early strength punya concrete. So kita sekarang ni banyak depend kepada sika dan sebagainya. So by introducing this geopolymer concrete, we have successfully installed and apply our product. So this is for the slump density, compressive strength. Okay. So this is some mechanical characteristic, flexural strength, etc. So I think this one nanti kita akan cover dalam kita punya practical training lah, right? Kita akan buat cost comparison dan sebagainya. So this is banyak application orang kata apa, roadways kan. Ini slipper, digunakan sebagai slipper untuk railway. Okay, geopolymer pipe, fire resistant geopolymer and etc. So this is some research conducted. Dan ni dia menggunakan fly ash, mirha and silica fume. Alright. Okay. Dan dia menggunakan sodium silicate and sodium hydroxide. Okay. So they try to see the effect of the curing method on the properties of the geopolymer concrete. Okay, ICM analysis. Ini image yang kata zoom ke dalam tu, kita menggunakan scanning electron microscope. I think this is too technical ataupun teori sangat kan. Nanti semua pakai tidur ni dengan puasa semua kan. Ini self compacting concrete. Alright. Self compacting concrete ni bermaksud you don't have to use maksudnya dalam keadaan fresh tu dia self compacted, right? It's similar to the traditional concrete, but the workability of the geopolymer concrete tu can be placed and compacted by itself, right? Of course, this workability influenced by the mixed proportion. Mixed proportion tu kita perlu buat nanti dalam training kita dekat next kita punya program, okay? And then okay, so this is all about the self-compacting. Alright, so this is some mixed proportion. Nanti dalam training tu saya akan ajar lah macam mana untuk buat all this mixed proportion. This is some kita go through je lah properties of the self-compacting geopolymer concrete. Okay, the bonding characteristic. Okay, yang ini kita gunakan geopolymer for the soil stabilization. Alright, sebab kita nampak dia kata apa, kita perlukan satu method yang advanced to improve the physical and mechanical properties of the soil. Alright, this technique actually it involve the injecting ataupun kita grout the geopolymer. Dia dalam keadaan fluid materials, alright, so dia akan flow into the spaces within the soil and into the ground lah, alright. And we have kalau tengok kat sini, this is method statement. Ini yang kita buat dekat one of the slope dekat Klang Valley, right? So ni slope dia jatuh, right? Dia jatuh, and then sebab dia backfill dengan pasir je, jadi dia tak ada binder. Jadi bila ada air dan sebagainya, dia punya slope tu dia collapse. So we inject with the geopolymer. Okay, so this is another problems. And ada satu lagi masalah, this one, a utility water pipe broke. Kalau kita tengok kan, bila berlaku pipe pecah dan sebagainya, tanah tu akan basah sekali kan. So lepas dia repair all this pipe, normally dia orang akan backfill je lah dengan tanah tanpa treat dulu that wet punya soil tu. So what happen bila dia orang dah backfill dengan tanah balik, and then dia orang pave balik jalan tu, and then kita datang esok kita nampak dia akan jadi potholes lah, ataupun dia akan jadi macam ada bump lah kat situ, right? Sebab bila pipe pecah, of course dia akan wet kita punya orang kata apa ni kan, tanah kita. So need to be effectively mended to avoid recurring problem. Okay, alright. So berlakulah localized settlement dan sebagainya. So what need to be done? So we turn this slurry into the strong soil. Ini tanah ni saya ambil daripada site, saya rendam dalam air satu malam, and then saya gunakan this geopolymer technology, and we get compressive strength 1 megapascal, which is 1000 kilopascal within 3 hours. Okay, so slurry campur dengan saya ada produce satu nano powder, and then mix with the cement and the polymer. Okay, so this is kita menggunakan teknologi nano powder. Nano powder ni saya buat daripada geopolymer juga. So kita ada absorber ni, kita akan mix with the slurry, and then we add some certain proportion of the cement and activator, then it completely harden and gain very high early strength. Dia macam konkret jadinya. Jadi bila tanah yang basah tu kita dah treat dia, so dia akan bukan sahaja dia avoid daripada surface of the road to become settlement, tetapi dia akan protect pipe tu tadi. Okay, ni saya tambah lagi dengan water saja, saya tambah lagi air dalam tanah tu, dan kita guna geopolymer based absorbent ni. Okay, and then kita mix. Then ni saya dah buat a few specimen lah, right, by varying the mix proportion, and then kita test lah dia punya strength. Okay, ada go the compressive strength, and kita tengok yang nombor, and then lepas kita dah buat test tu, saya rendam dalam air balik. Harden soil tadi tu rendam balik sebab nak tengok dia still intact tak after soaking tu tadi. Right, jadi kita nampak dia masih lagi in contact. So meaning that dia reaction tu memang involve fully where the grain of the soil tu pun involved in the reaction process, in the geopolymerization process. So tu into our setting time kita test, kita dapat 1 megapascal or 1000 kilopascal. Kalau ikut standard STMD 4609, kalau siapa yang involved in the soil strengthening or soil stabilization, so we can gain we need to gain at least 345 kilopascal lah. Tetapi bila kita guna our absorbent, geopolymer absorbent ni, within 2 hours kita dah dapat 1000 kilopascal. So meaning that very fast setting, high early strength punya ni lah. So this is some microstructure. Mesti buat microstructure ni bila kita involve dalam geopolymer, sebab kita nak monitor. This is how we monitor the performance of the geopolymer itself. Okay. Ini kita ada buat dia punya sequence of soil stabilization work lah. Okay. Lepas kita lepas dah pihak bertanggungjawab tu repair the utilities, lepas tu kita start treat the unsuitable soil inside the trench and soil compaction, and then kita layer sand atas tu, crusher and root pavement. Okay, so this is some method statement. Okay, so this is some kita kata mechanism ataupun schematic diagram lah. Okay, so that's all for the geopolymer. Okay, saya masuk sikit on the lightweight concrete. Okey lagi ke? Boleh continue ke?
Boleh doktor.
Kan, hari ni dengar saya beletiak apa tak tahu kan?
Okay. It's a good one. It's okay.
Okay. Tak apa, kita pun ada buat recording kan. So siapa yang nak tu, tapi ada sedikit kata apa management cost lah untuk recording video tu nanti kan. Dan untuk geopolymer tu nanti kita akan buat training. Saya akan ajar mix design untuk you buat. Lagi cantik kalau industri tu sendiri dia ada waste dekat site. Construction demolition waste ke, slag waste ke, ataupun yang baru ni dia orang jumpa saya, dia orang ada waste daripada apa dia panggil Allah saya lupa lah. And then bila saya buat chemical composition, saya check dia punya chemical content dia, content very high silica and alumina. So now kita tengah buat formulation lah untuk dia. Okay, so ini mana-mana industri yang berminat can come and contact us lah. We will discuss and we will try to do the preliminary study lah, right?
Okay. Doktor, ada a message from organizer.
Okay.
The link for attendance will be provided at the end of the session. So I hope everyone can sabar dulu, don't leave the session, because without filling in the link, you will not get the certificate.
Okay, all right. So please make sure all participants, make sure that you fill in the form in order to receive the e-certificate.
Yes.
Right. And so you akan receive CPD and CCD point kan, from BEM and also MBOT. Okay, so now I would like to introduce a little bit on the lightweight concrete. And again, untuk mix design, kita akan buat dekat training fizikal yang kita dah rancang dengan Jackford Consultancy. Sebab itu you kena attend secara fizikal. Tak boleh saya nak sembang cerita macam ni kan. Memang tak boleh nak buat sebenarnya. Ini saya just give kata apa, some overview ataupun the background of this kata apa, lightweight concrete lah. So I will continue with the lightweight concrete. I think most of you yang dah involved in the industry ataupun civil engineering background may be aware on this type of the concrete and experience with this type of with this type of the concrete. Alright, so what is lightweight concrete? Okay. So actually the name lightweight itself always give us answer, right, and clue what is meant by the lightweight concrete. So of course the lightweight meaning that the concrete is lighter than compared to the conventional concrete. Okay, but the issue and question is about the performance, all right, compared to the normal concrete. And how about the main design of this lightweight concrete? All right. So in order to have to produce this lightweight concrete, we need to find the suitable materials, suitable design, and the suitable formulation. And also we need to put into consideration also the cost. Kita tak naklah menggunakan lightweight aggregate for example kan, tapi costnya terlalu tinggi. Siapa nak guna kan kita punya lightweight concrete. So we need to consider all these items, right? So as we can see in this slide, actually picture tu adalah daripada lab saya. Saya dah successfully produce this lightweight concrete with high strength and high performance. This lightweight concrete saya boleh achieve 50 megapascal, right? And yeah, it can float in the water. So the density and strength is balanced, right? Normally kalau kita refer to the standard, the density of the lightweight concrete ni should be less than 2000 kg per meter cube. However, in order to make our concrete to float, maksud nak bagi dia terapung atas air kan, kita kena make sure that our density less than 1000 kg per meter cube. Baru dia boleh timbul macam dalam gambar tu lah. So the idea is very simple, alright. We need to make sure that yeah, of course, for the concrete to float, of course, the materials inside the concrete should be light lah. Betul tak? Dia kena ringan lah. Tak boleh lah kita guna bahan yang berat tetapi nak concrete yang ringan. So itu memang konsep yang salah lah. Alright. Okay. So actually we have 3 types of the lightweight concrete. This is one of the example ataupun types of the lightweight concrete. So number 1, lightweight aggregate concrete. Okay. So yang dah digunakan dekat industri, normally dia orang ada menggunakan cost aggregate, lightweight cost aggregate. For example, Leka, kita ada a few Pumice, Shale, etc. lah. Kalau betul dalam gambar tu ada macam-macam lah. Tetapi yang kebanyakannya yang digunakan sekarang ni adalah Leka lah, right? So the component or the factor that contribute to the lightweight concrete aggregate ni adalah the aggregate itself. Okay, so when we utilize the lightweight aggregate, it will produce the lightweight concrete, right? So the second one is the lightweight foam concrete. Okay, lightweight foam concrete ni normally we will use foaming agent. Foaming agent ni senangnya air sabun. Pasal tak kalau kita pergi basuh kereta kan, kalau lah siapa-siapa nak try buat sendiri kat rumah, you beli simen, you beli pasir, you mix dengan air, kemudian you masukkan foam tu. Pergi dekat kedai parking, kedai apa cuci kereta tu kan, you boleh buat sendiri je kat rumah. Tetapi the right proportion, the right design, the right method, tu nanti you kena datang dekat training kita. Kita akan ajar you macam mana buat lightweight concrete secara hands on. Okay, tapi kalau nak try kat rumah boleh je, tak ada masalah. You can do by yourself, right? And then satu lagi kita ada lightweight structure concrete. Okay, and then this is yang very special yang saya tengah buat sekarang ni bersama dengan kata apa, Petronas Research, sebab dia orang nak gunakan sebagai oil well punya application, right? Untuk CCUS punya well chamber tu dalam laut tu. So this is actually we are need to make sure that apa nama, material yang kita guna tu adalah ringan lah. Tetapi for this kind of the lightweight concrete, saya produce lightweight binder, simen tu. Saya suka simen. Kan? Tak tahulah, saya ni kalau cerita pasal konkrit ni, saya suka nak ke arah nak attack simen tu, sebab saya rasa yang itu yang the main materials dalam konkrit yang akan give significantly significant contribution to the concrete properties. Okay, so this is actually saya menggunakan Chinosphere. Okay, ni saya ambil dekat stesen jana kuasa elektrik dekat Kapar. Banyak kat situ, kita tengok dia punya apa nama Chinosphere dia. Okay, so this Chinosphere is actually it's a type of the material yang kita combine dengan konsep of the geopolymer tadi, right? And then tetapi very little literature kalau awak tengok dekat ResearchGate dan sebagainya yang reported on the influence of the Chinosphere ni, right? So based on our experimental work on the Chinosphere ni they have very low density, tetapi dia boleh add dengan alkali activator dan jadikan sebagai binder for the concrete. So instead of the binder, dia akan jadi agent sebagai lightweight punya contribution tu tadi, alright. Dan dia pun memang very good mechanical strength and low thermal conductivity. Okay, and dekat luar negara, Hirajima daripada Jepun, 90% of the Chinosphere tu dia punya diameter dia dekat sana in between 100 to 420 micrometer lah. Yang lain bottom ash, molten slag dengan fly ash tu, yang tu kita guna dalam geopolymer biasa. Untuk lightweight geopolymer, kita kena incorporate dengan Chinosphere. Ini fly ash yang daripada Kapar, Jimah dengan Manjung lah. Okay, so this is Chinosphere. So kita dah check dia punya spherical shape, dia punya density, resistant against oxidative and corrosive environment, thermal conductivity, and also dia punya mechanical strength. Okay, so this is some chemical composition of the concrete tu. Okay. Okay, so kalau kita tengok this kata apa, lightweight menggunakan Chinosphere ni, actually this Chinosphere is a new tau. Dekat Malaysia pun dia orang buang je, tak ada siapa yang guna lagi. It's very lightweight. The density is about 500 kg per meter cube. Okay, can you imagine? Very lightweight. And it is in hollow sphere, which composed largely of the silica and alumina dekat dia punya surface, dekat dia outer surface of the Chinosphere tu. And then kita check dia punya density very low and high thermal insulation and high strength to weight ratio. So when we incorporate Chinosphere into the geopolymer matrix, the result is very surprising because kita dapat concrete yang light dan juga high strength, kan? So very best lah bila kita boleh reduce the overall density of the concrete by using this waste. Sebab waste ni kan susah juga kalau kita nak cari yang lightweight, kan, betul tak? Tapi yang ni kita jumpa dan kita nampak very high and very good potential lah. And also the airfield dalam Chinosphere tu can contribute to enhance the thermal insulation properties, so making this material suitable for application that required good thermal resistance. Also it can enhance the fire resistance, and of course in terms of the environmental benefit, when we utilize this fly ash byproduct from this coal combustion yang saya cerita tadi tu, daripada pembakaran arang batu tu tadi, helps in waste management and reduce the reliance and dependence of our construction industry to the Portland cement, thereby will decrease the CO2 emission. Okay, so a lightweight binder by using this chinosphere fly ash is a new type of the composite materials yang kita use in the production of the lightweight concrete, and the binder itself creating by incorporating chinosphere. Mungkin saya boleh share, saya ada buat apa nama? Okay, this is the mixed proportion yang saya buat with my student. So nanti dalam training tu kita akan ajarlah macam mana kita nak dapatkan the proportion of the cement, water, chinosphere, lightweight, sebab dia tak sama dengan konkrit biasa. Sebab kita perlu menggunakan kaedah solid volume fraction. Iaitu yang you perlu datang, dan kalau siapa yang berminat lah, datang dan kita akan guide you one by one, and you masuk lab hands on, you produce your own lightweight concrete. Okay, so I think sampai situ dulu kot. Kalau nak cerita banyak lagi ni, takut semua dah boring dah ni. Saya dalam kelas 45 minit je, tak lebih. Okay, so I think that's all from me. I hope to see everyone, siapa yang berminat untuk further enhance knowledge on the mix design dengan practical punya session. Kita akan buat hands on punya kata apa session dekat Unicell. Okay, saya akan datang untuk, ada beberapa trainer yang lain lagi lah. So kita akan produce, tadi kita ada lightweight concrete, kita ada self-compacting concrete, and then kita ada high strength concrete juga. Okay, so insyaAllah hope to see you, and rasanya tak lambat lagi kot untuk saya ucapkan salam Ramadan pada semua. Okay, so maybe kita ada Q&A mungkin sebelum saya.
Okay, thank you Dr. Warid. So
Okay.
I think we can open for the Q&A session now. We have enabled the mic, so anyone could just on the mic and ask questions if you want, or you can also place your question in the Q&A sections or also in the chat box. Sebab tak ada banyak sangat kan, tadi takut confused, so we want to like focus on the chat Q&A sections too. But it's okay, since there's not much of questions from the audience. So perhaps we can just on the mic or just put in the chat box. Anything that is convenient to you guys. Semua puasa kot doktor. Slow sikit.
Tak apa, it's okay. Kalau ada soalan after this pun, you can email to me or you can direct to the organizer, no problem.
Okay, sure. So
Okay.
Maybe you want to promote your next yang hands-on tu, the date ke? Dah ada date ke? Macam mana?
Yang date tu nanti kita akan update dengan semua peserta yang berminat. Sesi cumanya untuk next tu bulan 7 kita ada hands-on untuk apa nama mix design for the normal concrete. Yang tu kita bagi certification dengan CIDB sekali lah.
Okay.
Itu for normal concrete. Maksudnya kita akan keluarkan orang kata apa, certificate for mix design, and also workability. Kita akan buat sesi pagi tu mix design of the normal concrete. Sesi petang tu kita buat slump test dan juga compression test.
Okay. That one will be in July. The one yang dekat Unicell ni belum ada date doktor?
Itu kita tak confirm lagi dia punya tarikh.
Okay.
Nanti kita
So
akan
you guys
update
can stay tuned for the advertisement lah later.
Okay, sure. No problem.
Okay. So any questions from the floor? Tak ada.
PS Azmin memang lecturer dekat Unicell ke?
Saya lecturer Unicell. Yes.
Oh, okay. Bidang apa?
Okay. Saya sebenarnya background saya chemical engineering, tapi saya duduk di bawah civil engineering. So it's a bit jargons dia tu macam it's not really my language, tapi saya tengah buat PhD pun dalam concrete juga. So I am very
Very
interested
good.
lah dengan your presentation ni
Ya,
sebenarnya.
sebab geopolymer ni actually yang the first dia punya geopolymer ni is actually coined by Joseph David Ovid. This Professor Joseph David Ovid ni actually is a professor in chemist. It's not
Ah,
from the civil, it's not from
yes,
the
yes.
material. He is a
Okay.
chemist.
Okay, okay.
So he is the one who coined this geopolymer.
Okay. Alright, alright. That's something
Okay.
good to know. Okay. Tak ada soalan
Okay,
saya rasa ni, Doktor.
tak apalah.
Doktor, Assalamualaikum.
Okay.
Ya, waalaikumsalam.
Ya, saya Muhammad Fauzi Zakaria daripada Kuala Terengganu.
Okey, Engineer Muhammad Fauzi. Silakan.
Nak tahu yang your geopolymer concrete, can we use
Okay.
for the strengthening crack concrete?
Actually, kita punya mix design for the geopolymer repair material in form of paste tu, dalam bentuk paste. Memang kita guna for grouting concrete. For the grouting untuk concrete crack. Tetapi sebab kita buat tu memang untuk design for the fast setting and high early strength.
Any case study yang doktor dah buat to the actual structure yang crack? Projek mana?
Ada.
Dah ada dah.
Nanti boleh email saya, nanti saya send details. Mungkin saya boleh share some reports untuk review by Engineer Muhammad Fauzi.
For the structure concrete yang corroded reinforcement, can you use this?
Boleh. Cumanya untuk kalau reinforcement yang corroded tu, kita kena buat kata apa, treatment dululah. Dan kita kena tengok condition of the reinforcement tu dulu.
Yeah.
Sebab kadang ada setir tu dia memang dah, bila kita pegang pun dah lerai kan. Itu we need to place the reinforcement first, and after that kita boleh direct. Tapi kita tak perlu, kalau geopolymer ni dia memang akan create satu layer, protective layer dekat surface of the reinforcement tu. Yang lain daripada tu, yang kita dah guna untuk repair potholes jalan, yang untuk rigid pavement lah. So kalau untuk yang kalau kata Engineer Muhammad Fauzi ada site mana-mana yang kita nak boleh try, kita boleh je bawa kita punya produk, we can demonstrate lah. Kita boleh try mana-mana site yang boleh access tu.
Memang adalah, saya ada satu projek yang di Primula Hotel, yang West Wing tu dia lama tak guna, tapi sekarang memang banyak konkrit dia crack lah.
Boleh, kita boleh guna, no problem. Kan? Kita boleh try apply, mungkin engineer boleh set kat mana tempat yang kita boleh pergi untuk apply kita punya produk tu, and then kita boleh terus tengok lah dia punya kesesuaian dia tu kat situ.
How about the cost of repair use geopolymer ni, Doktor?
Dia kalau itulah, dia sebenarnya costnya dekat simen tu memang tak ada lah, sebab kita memang tak guna simen langsung. Cumanya cost on the chemical tadi tu. Tetapi yang itu kalau kata kita untuk let's say kita katakan substrate, complete substrate kita tu grade dalam 20-30 kan. So saya boleh buat formulation yang kata apa, rendah je lah, tak perlu kita nak menggunakan kata apa, kita punya solution tu banyak sangat.
Tak apalah.
Just sesuai dengan kita punya substrate strength. Kan?
Okay.
Boleh, no problem. Sebab tadi pun Prof Adeyemi pun yang saya duk buat research dengan dia pun, kita ada guna alternative activator juga yang memang sangat-sangat murah. Tapi kalau engineer kata apa, concern about the cost, then kita boleh try both lah.
Yalah, pasal kita pun client remind to us to
betul,
cost yang kata yang sesuai lah untuk bajet dia kan.
Betul. Tapi kalau compare dengan Sika, kita murah lagi lah. Murah lagi. Tapi kalau compare dengan 3-in-1 yang dekat kedai hardware tu, kita mahal sikit lah.
Yalah.
Yang itu RM18 je satu beg kan.
Pasal sekarang pun saya banyak guna Sika produk for the
betul.
repair.
Betul. Tapi kita murah lagi daripada Sika lah, sebab Sika ni dia lagi satu Sika ni dia punya bonding dekat antara substrate dengan repair material tu dia agak ni sikit guys tu, dia boleh respawn balik.
Your cement ni boleh penetrate the concrete asal. Bila kita sapu yang crack tu, yang concrete
kita
poros kan, memang dia boleh penetrate.
Boleh, maksudnya nanti kita dia akan feel. Dia akan feel the porosity and crack yang ada tu. Jadi kita punya workability of geopolymer tu kita kena optimize lah. Sebab kita nak pastikan dia boleh seep through tiny punya space untuk crack tu kan. Sebab crack ni pun banyak size juga, ada yang kecil, ada yang besar. Kalau yang besar tu okey lah, tak ada masalah. Yang kecil-kecil tu so kita kena control lah dia punya workability, dan kena ada pressure, grouting punya pump tu kena guna jugalah.
Ya. Doktor, boleh I get your handphone number?
Sure kan. Boleh. Nanti nanti saya PM engineer.
Pasal saya selalu pergi kat UiTM Civil Department tu. I pun student
master. Boleh lah jumpa.
Buat master dekat sana. Part time.
Dengan siapa?
Dr. Rohana.
Dr. Rohana. Prof Dr. Rohana. Dia bidang kayu kan?
Kayu dengan buluh.
Kayu dengan buluh. Okey, boleh. Anytime kalau datang bagi tahu. Nanti kita boleh borak panjang. Dan saya boleh bawa juga pergi tengok tempat-tempat yang kita dah install kita punya produk tu.
Okay. Thank you, Doktor.
Okay. Welcome, Engineer Fauzi.
Okay, thank you very much, Engineer Fauzi. Ada lagi ke soalan? Tak ada.
Tak ada, kita tutup dululah.
Tutup okay. Alright. Saya rasa admin dah post link untuk feedback form whereby we're gonna take the list from feedback forms for your certificate of attendance. So please make sure that you fill in the feedback form so that you will receive the certificate later. Right, so we will probably give about half an hour for you guys to fill in the form.